one-dimensional heat conduction through composite wall. An induction furnace wall is made up of three layers, inside, middle, and outer layer, with thermal conductivity K1, K2, and K3 respectively as shown in figure. Determine the nodal temperature. Okay, let us analyze this using ANSYS Workbench. Here we have a three layers and we have a three thermal conductivity is given K1 8.5 watts per meter Kelvin, K2 0.25 watts per meter Kelvin, K3 0.08 watts per meter Kelvin, and thermal coefficient, convective coefficient is given as 45 watts per meter square Kelvin, and ambient temperature is given. Okay, we have four number of nodes here, and the first node is insulated and is having a temperature of 600 degrees Celsius, and the last node, fourth node, is have a convective coefficient. It is undergoes a convection. Now let us analyze this using ANSYS Workbench. Now in ANSYS Workbench, let us select it is a steady state problem. Here the temperature are not changing with respect to time, so that I'm considering the steady state here. If the temperature changes with respect to time, we should go for the transient state. Okay. Now it is steady state thermal, so I'll select the steady state thermal. Go to engineering data, edit. I'll give the first material as material 1. Material 1. Now the isotropic thermal conductivity I'll select. The first material, as we noticed in the problem, the first material thermal conductivity 8.5, second 0.25, and third is 0.08. But you see the units is watts per meter Kelvin. Okay. So now the first material I'll give this as 8.5, 8.5, but it is watts per meter degree Celsius. So I'll convert it to watts per meter Kelvin. Similarly, I'll go for second material, material 2. For this, select the isotropic thermal conductivity, and the isotropic thermal conductivity value for second one is 0.25. It is watts per meter Kelvin. Watts per meter Kelvin. Similarly, I'll go for third material, material 3. Now it is isotropic thermal conductivity. So I'll select here. So its value is 0.08 watts per meter Kelvin. So now we can select here 1, 2, and 3 layers is given. Now I'll go for project. Select here geometry, new design modular geometry. Here I'll select the XYZ plane for this problem. YZ plane. Look at here. What I'll do here is I will consider rectangle, as I am assuming the area of 1 meter square. So now I'll go to sketching rectangle, draw a rectangle. You can draw a rectangle, and now I'll give the dimensions general. So this length and this one. Okay. So the length, the area I'm concerned is a 1 meter square. So H1 be 1 and V2 be 1. Okay. So now we can see the rectangle is created. Now what I should do is, here you can see the problem. Here the first length is 25 centimeters, second 5 centimeter, and third is 3 centimeter. We should convert it to meter because we are doing the entire problem in meters. Okay. So your 25 centimeter is equal to 0.25 meter. 5 centimeter is equal to 0.05 meter, and 3 centimeter is equal to 0.03 meter. Okay. Now what I will do here is, the first element you can see that I should do the extrusion. The length of extrusion first is 25 centimeter, that is 0.25 meter. Okay, you can see here. First, what I'll do here is the sketch is created here. Next, I'll go for the extrusion. Before that, I'll revolve this the X direction. Okay, extrusion. Now apply the length, the depth of the first one, as I told that we should give 0.25 centimeter. So 0.25 meter, sorry. Now I'll give generate. Now you can see that I'll go for evolve option, that is created here. And the second layer, I should create the second layer here, so that I'll select the face. So I'll go for the face, select this face. Now again, I should change the plane, and now go to this option. Now what? Go to zoom option. Okay. Now what I'll do here is I'll select Again sketching. Now before that I'll generate. Go to sketching. In sketching again rectangle. So now select the rectangle from this correctly to this. Okay. Now again I'll go for the extrude option. Generate. Go to extrude. Extrude. Here I should select the add frozen because I'm considering second material add frozen. The extrusion depth of the first second one is 5 centimeter, that is 0.05 meter. Now we generate. Generate. Now you want to see that we can see that second material is created here. Again, we have a third layer. Similarly, same. Now I'll go to the face option here. Select this face and again plane. Change the plane here. Then again draw the give generate sketching. Draw the rectangle from this point. Again, I am drawing the rectangle. Rectangle and then give generate and then I should extrude this one. As I told to how to extrude. To extrude again I should change to add frozen. Third material we have the 3 centimeter, that is 0.03 meter. So I change it to 0.03 meter. Now give generate. Now I'll revolve and I'll check 3 layers is being created. You can see here we have 3 layers here. One, you can see here 1, 2 as well as the 3. 3 layers is being created. After this I should go here. We can 3 parts is created. Select solid 1, 2, 3 and now give the new part. We have created the new part. We can see the 3 layers here. Okay. This completes the second step. Now I'll go to the third step. Close this. To model, right click edit. In modeling, first select the geometry. In geometry, part we have 3 parts. Okay, so sides are solid. So by default it will be having a structural steel. So now I should convert to first one is material 1. So I'll select material 1. Similarly solid second. So I'll select that material 2. Third I'll select this again material 3. Now I go for meshing. Mesh. In meshing, as we can see that element order is programmed. So I'll change it to linear. I'll change it to linear. Then element size, I change it to now otherwise mesh. Generate mesh. Give generate mesh. So you can see that the mesh is being generated here. If you want this to change the element size, that is I'll take it as 25 mm. 25 mm. This I'll change it to 25 mm. 25 mm. So now mesh is created. After this, we should apply a boundary conditions. Okay, we should apply boundary conditions. Now, this was boundary conditions. Go to steady state thermal environment. In environment, as I told that the first here you can see that the first node is been insulated and applying a temperature of 600 degrees. So first I'll apply these boundary conditions. Now I'll select conditions. It is perfectly insulated. So this is perfectly insulated. Now I select this space and I select this space and give here you can see type perfectly insulated. I'll give apply. Okay, so you can see that it is perfectly insulated. Now at the same node, I'm applying a temperature of 600 degrees Celsius. Now again here steady state insert temperature. So insert temperature at this space only. This space only I'm applying a temperature, but the temperature is of 600 degrees Celsius. 600 degrees Celsius, but you can see that we have a Kelvin here. So units are very important. So I'll change it to degrees Celsius. Here we can see that okay, we have Kelvin and Celsius. I change it to Celsius. So now you can see that what is Celsius is given 600 degrees Celsius. Temperature is given. Now I select this plane and I'll give apply. So the temperature of 600 degrees Celsius is applied. Okay. So first boundary condition is completed. Now at last phase that we are applying the convection. Now I'll go to revolve option. Okay. This phase. Now I'll go for the convection. Here you can see the convection. Convection. Select the phase. This is the phase which we are applying the convection. So in a convection, we should give film coefficient, that is H, and ambient temperature. See the units here. It's having a watts per mm square per watts per meter mm square degree Celsius, and ambient temperature is 22 degrees Celsius. In the problem, you check that we have the H as 45 watts per meter Kelvin, meter square Kelvin, and the infinity as 30 degrees Celsius. So I'll convert it to Kelvin first. Okay. Now here, so what I'll do here is I'll change this one watts per, here I'll change to Kelvin, and I'll change to watts per meter square. So I'll change to meter here. So you can see that watts per meter square Kelvin is changed here. Now give the coefficient as 45. 45 watts per meter Kelvin. And now here in the problem they are given the 30 degrees Celsius as ambient temperature, because we change it to Kelvin. So Kelvin means we should add 273. 30 plus 270 is 303. So I'll give 303 here. 303 Kelvin. Now I should select the phase. This place we are applying the convection. I'll give apply. You can see that convection of 303 Kelvin, and the ambient temperature, and this is the thickness film coefficient we have given here. So this completes the boundary condition. So heat flow, that is we have given the insulation temperature we have applied of temperature, then we have converted to convection. Okay. Now this completes the boundary condition step. Okay. Now I should determine the temperature, nodal temperatures. So what I'll do here is, the main intention of doing a thermal analysis is to determine the nodal temperature. Now I'll solve this. Solution is done. Now solution, insert thermal temperature. Now solution, evaluate all results. Now we can see the different temperature here. Okay, these are temperatures. You can check the temperatures. This is one temperature 873.15, and here we have temperature, and the minimum temperature is 323.16. Now what I will do, I want to check at each node. If you want means, again I can go to the results. Here we have a probe, and you can see each and wherever you require, you can check the temperatures. Okay, this is the temperature. This is this. Now insert. Insert here also you can go for probe and temperature. Evaluate all results. This is the different temperatures. Okay. If you want to see in Excel, the solution, worksheet result summary. So here you can check the minimum temperature is 323.16 Kelvin, and maximum is 873.15 Kelvin.